Now we're going to dive into the Bronsted-Lowry paradigm in a little more detail, and focus especially on acid dissociation equilibria in this video. We're also going to introduce the P operator, which is going to be convenient for us when we start to quantify and treat quantitatively acid-base equilibria. I want to start though by revisiting the self-ionization of water. Water has the property of being amphoteric. This means it can act as both an acid and a base. It can act as an acid because it has a proton within it that can be surrendered to a solvent, and it can act as a base because it can accept a proton using one of its lone pairs. Since water can act as an acid and a base, one molecule of H2O can act as an acid with respect to another molecule of H2O, which acts as a base, and this gives rise to the self-ionization behavior of water. One molecule of water acting as an acid can surrender a proton to another molecule of water acting as a base, and the resulting products will be the conjugate acid of water, H3O plus, aqueous, and the conjugate base of water, OH minus, aqueous. To write the dominant reactions of Bronsted acids or bases in water, we replace one of the waters with either HA or B, and on the product side, we replace either H3O plus with the conjugate acid of the base or OH minus with the conjugate base of the acid. For example, for a general acid dissociation equilibrium, we replace the acidic water with aqueous HA. Leave the other water in place, which will serve as the base here. On the product side, we'll still have the conjugate acid of water, H3O plus, because water is accepting a proton from the acid, and we'll have, instead of hydroxide, the conjugate base of the acid itself, A minus. Similarly, for a base association equilibrium, we put the base in, and we also have one molecule of water on the reactant side. A proton is transferred from the water to the base, so we have the conjugate acid of the base as one of the products, and hydroxide as the other product. Since these reactions proceed to the right to some degree, these equations show us how, for example, a Bronsted acid increases the concentration of hydronium in solution, and a Bronsted base increases the concentration of hydroxide in solution. For an acid dissociation equilibrium, an acid reacting with water to form H3O plus and A minus, the key equilibrium constant is known as the acid dissociation constant, Ka. Ka is the equilibrium constant for both of these processes. The reaction of HA with H2O to form A minus and hydronium H3O plus, or the equivalent reaction HA forming aqueous A minus and the solvated proton H plus. Remember, we've treated H3O plus and H plus aqueous as equivalent species. Since we're going to be dealing with acidic solutions in equilibrium, it's important to understand the form of the equilibrium expression, which is equal to Ka at equilibrium. And the form reflects what we've already seen, products over reactants. On the product side, we have hydronium, as well as the conjugate base of the acid, A minus, and we have HA on the reactant side, aqueous HA. Using this equilibrium expression, we can begin to develop intuition for the size of K and what that means on the microscopic or molecular level. A large Ka, that is to say a Ka value much greater than 1, indicates a large degree of dissociation at equilibrium and that products are favored. This is a general idea from chemical equilibrium that we've seen before. If we look at the equilibrium expression, if Ka is large, then at equilibrium the concentration of H3O plus and the concentration of A minus will be much greater than the concentration of HA. On the other hand, if the value of K is small, such that it's much less than 1, there's a small degree of dissociation at equilibrium, and the reactants are favored. And again, this is a general idea from the theory of chemical equilibrium. Based on the form of the equilibrium expression, if Ka is much less than 1, then the concentration of HA will be larger than the concentrations of H3O plus and A minus at equilibrium. Ka values can span a huge range in practice, from 10 to the negative 50 to 10 to the 10th power. These extremely tiny and extremely large numbers aren't terribly intuitive, and so what would be helpful here is a more intuitive number that's a little more human-friendly. To get to a more human-friendly number, we can use what's called the P operator. It's more intuitive actually to work with the exponents themselves rather than worrying about 10 to the negative 50 or 10 to the 10th power. To get the exponents from the actual Ka values, all we need to do is take the logarithm, And since most Ka values are actually less than 1, it helps to take the negative base 10 logarithm. This is what's known as the p operator. P corresponds to the negative base 10 logarithm operator. To recover x from px, we take 10 to the negative px, and this gives us x. This is just essentially inverting the equation above by raising both sides to 10 to the negative power. pKa value, Ka values to which the p operator has been applied, are much more brain-friendly. The range on the last slide goes from 10 to the negative 50 to 10 to the 10th to 50 to negative 10. But one of the tricks here is that since we are multiplying by negative 1, we need to invert our intuitions for Ka values. In other words, a low pKa value, like 10 to the negative 10, corresponds to products favored, mostly dissociated H3O plus and A minus at equilibrium, while a high pKa value corresponds to very little dissociation and reactants being favored at equilibrium such that mostly aqueous HA is present. And because concentrations are related to Ka, it would also be helpful to use P in front of the hydronium and hydroxide concentrations, and this is how we define pH and pOH. pH is equal to the negative base 10 logarithm of the hydronium concentration, and pOH is equal to the negative base 10 logarithm of the hydroxide concentration. Because of the negative sign here, we need to again sort of invert our intuitions in terms of acids, bases, hydronium, and hydroxide concentration. Acids decrease pH since they increase the concentration of hydronium, and bases increase pH since they decrease the concentration of hydronium. That's represented here by the pH scale. You'll notice that at each point on this scale, the pH and pOH sum to 14, and that must be true because of the nature of Kw. Kw is 10 to the negative 14, and it's equal to the product of H3O plus concentration and OH minus concentration. That means that pH and pOH, which comes out when we apply the p operator to both sides of this equation, must be equal to 14. And that's true at every point along this scale. On the right, we have basic pH values, where the concentration of hydronium is less than 10 to the negative 7, and on the left we have acidic pH values, where the concentration of hydronium is greater than 10 to the negative 7.